We're very honored and privileged to have our 2006 paper, Architecture-Based Self-Adaptation in the Presence of Multiple Objectives, recognized by SEAMS 2020, 14 years later, as its 2006 most influential paper. My name is Cheng. After finishing my doctorate and a year of postdoc, I spent 6.5 years at NASA Jet Propulsion Laboratory, engineering satellite software, and a little over 4 years so far at Uber Advanced Technologies Group, engineering safe self-driving technology. I continue to find ways to apply research ideas from the areas of software architecture, self-healing systems, and multi-objective trade-off analyses.
And I'm David Garlan. I'm a professor and associate dean at Carnegie Mellon in the School of Computer Science. I've been there for a long time, and I've been working for the last decade or two in the area of self-adaptive systems, and happy to be collaborating with the co-authors on this paper and many other students.
I'm Bradley Schmerl. I'm a principal system scientist at Carnegie Mellon as well in the Institute for Software Research. I'm also really chuffed that we have been given this award. It's an honor, and it's been great to sort of work on this project for the last, and related projects for the last 20 years.
And needless to say, our thanks go to numerous people and collaborators who have worked on this over the years. In this video, we're going to take a roundtable discussion approach over a few themes, approximately 3 to 5 minutes each, and we do hope you enjoy it.
So this paper, as you said, Owen, is about self-adaptation, architecture-based self-adaptation in the presence of multiple objectives. I wonder whether you could kind of tell us a little bit about what the paper was about, and what the context of the world was at the time when we wrote this paper, and those kinds of things.
Yeah, sure. So to set the context, at the time we sort of recognized that systems were becoming more complex and sophisticated, and with that, the cost of ownership was going up and largely going into system administration, with the implications of both cost and quality of the system. So that it motivated this general idea, are there ways that we can automate more of what system admins do? So the system that we discussed, described in the paper, it concerns a framework we call Rainbow, which supports self-adaptation in a generic way. So the central idea of Rainbow at the time in 2006 was already formed in our previous publications. It really follows the IBM Autonomic Computing Initiative MAPE K-loop. This came out around 2001 or so. So importantly, the K is represented by the runtime software architecture model of the target system, its architectural style, the associated constraints, and the available architectural operators. And so we wrote this paper from our observation and interviews of system administrators and how they perform their tasks, from which we really recognize two needs. One is to automate the mundane and routine system admin tasks and scripts. And then the other one is from recognizing that they actually balance multiple objectives when they're doing their job.
So as you say, sort of the key idea, or one of the key ideas here, is this idea of multiple objectives and being able to trade them off and balance them. And I'm wondering where that idea kind of came from. What's the sort of heritage of that idea? David, do you have ideas?
Yeah, well, we know that one of the most difficult things about complex systems is there are multiple qualities that you care about, and very frequently they're in opposition. So you can improve the security, but at the cost of performance. And we've known about that for a long time in the context of things like architectural design, where we often have to make choices about system structure based on explicit trade-offs in terms of qualities. And so in some sense, adopting this idea of multi-dimensional quality was a very natural transition from design time into runtime, where we needed to be able to consider the fact that in a given context, there are many ways you might adapt a system. The right way to do it involved making the right trade-offs among a set of dimensions. And so we want some way to explicitly be able to designate those dimensions and to be able to characterize the different sorts of trade-offs that we're willing to make.
You talked about one of the other key sort of aspects of this work is the focus on sysadmins to get ideas about how to automate their work. And I'm wondering, you talked about cost being one of those things, and I'm wondering whether there are other things that you also considered when you were sort of thinking about automating their work.
Yeah, so actually, it's interesting what we know from, and actually IBM published this in their autonomic computing initiative, is that a big part of the cost of system ownership that it goes into system administration is actually due to the errors that humans commit when they administer the system. Basically because humans are basically prone to committing errors in these really mundane tasks and routine tasks, right? It's part of it is because of boredom, part of it is because of repetitiveness. So what we realize is that if we can reduce the number of these mundane tasks that are done by humans, then not only do we reduce costs, we also can improve the quality of the system overall.
Okay, so so when we talk about automating what sysadmins were doing, we have to have some way of expressing what it is that they do, and that leads us into sort of the other important aspect or the key contribution of the paper, which is this idea of stitch as a language to automate self-adaptation. So I'm wondering whether you could tell us a little bit about stitch as it appears in that paper.
Yeah, so for sure. So the first version of this language, stitch, actually, it appears in this paper. It separates out the concerns of automation, right? So we observed how sysadmins do their job, and from that, we tease out the various sort of parts of that system administration task. So while separating out the concerns, and I'll briefly mention these are sort of the operators, the tactics that uses operators, and then strategies that sort of incorporate a number of different tactics to accomplish a certain result. We do this, or the language stitch allows you to do this while also applying multi-objective reasoning. I should also note that this is the first paper where we describe what would eventually become ZNN. In this paper, we call it Z.com. So if I could go into a little bit of what the stitch language embodies, there are 4 core ideas. First is control theory. This is where we recognize that the results of an action taken on the system may be uncertain. So we need to enable those results to be observed before the next action is taken. The second core idea is that the operations are going to be asynchronous. So we actually need to apply timing, and we use settling time to allow for these asynchronous operations to complete. The third key idea here is that of uncertainty, because, well, the outcome, the result, may not be one way or the other, right? So we capture these with probabilities, which are represented in the strategy tree. And then finally, it's the application of utility theory. This is the key semantic principle that lets us quantitatively compare the alternative strategies that are available for adaptation.
If I could jump in a little bit here, I think, you know, when you talk to administrators, you realize that when they solve problems, there's often a fair amount of uncertainty of how they go about that. And when they approach solving a problem, they may try one thing. If that works, that's fine. If it doesn't work, they're going to try something else. And so they orchestrate a sequence of decisions and actions that they have to take into consideration, partly because they don't know exactly what's going to happen, but also because they want to favor certain kinds of qualities over others if they can, but they can't always achieve that. So I think this is an important idea that suggests that if you want a way to represent what operators do, you have to embody a set of concepts in a language that are quite different than you might find in ordinary programming language. We could, in principle, have simply programmed adaptation using Java, but instead, what we wanted to do was something that matched up the cognitive processes that we were trying to emulate with the language for expressing those ideas.
Right, and I think the utility theory idea came out of the idea that you needed to somehow be able to compare all these different things that they would do in a quantitative way, and sort of this trade-off was encoded in this idea of this utility theory, where you can kind of understand what the impact of the strategy is going to be and what the preferences are of the sys administrator at the time, or Rainbow now, how they balance those preferences. So we've talked about what the paper contains, and I'm wondering whether you have any thoughts about what you thought, sort of going beyond the paper, what the enduring principles are that might still be relevant today. David?
Yeah, I think, one of the reasons a paper gets an impact award is because the things in it go beyond the specific technical details. So it's definitely an important question to ask. And I think if you step back from the paper, you can see that there are two levels of enduring principles. One is at sort of the abstract level, the general notion of adaptation and the kinds of architectures to enable that. Specifically, when we look at the approach that we're taking, along with others, there's the idea that you want to decouple the adaptation mechanisms from the system itself. And this is in contrast to most systems that were built before, let's say to deal with fault tolerance, where you would embed the recovery mechanisms directly in the system. And so the advantage of separating things out was you could then reason about those, you could potentially reuse those ideas across different systems, and you could engineer those somewhat separately from the system, so that you didn't have to have foresight when you built the system entirely in terms of what you might do for adaptation. So that was the big idea number one, I think, is the separation of concerns. A second big idea here was that adaptation can be done in an ad hoc way, and has been and was done, but we wanted to have a generic approach that would enable the engineering of adaptive mechanisms on virtually any system. And that led to an idea of a framework that could be instantiated at low cost to provide adaptation to a particular system. And so it was important that we invested in both the engineering and the design of this framework so that it had the right dimensions of pluggability, and that it could be actually used in a variety of contexts, a variety of business contexts, a variety of technical contexts. So those are two big ideas. I think the third idea was that when we're working in this kind of system, we really need to deal with uncertainty as a first-class entity. In many cases, the world of programming as we know it assumes that things happen in a kind of deterministic way, or at least you can approximate what goes on deterministically. And we were able to adopt the fundamental notion that no, there's going to be a lot of uncertainty, and coping with this in an explicit way was critical. So those are the ones that come to mind right now.
I think also another one was this idea of having architecture as the sort of central reasoning mechanism here in Rainbow, where you sort of realize from sort of architecture research and architecture work that the runtime architectural structures of a system give a way to reason about the trade-offs for making architectural decisions at design time. And so this sort of translated naturally to thinking about how you would do that trade-off analysis at runtime as well. And so the architecture and model, sort of a key core aspect of the work, sort of certainly in the beginning. And I think the architecture is recognized still as kind of one of the central models that you want to consider if you want to consider adapting your system.
Indeed, and I think, you know, if you look at the way control systems are built, as the control mechanisms are reasoning about the state of the system they're controlling, the models they have are much simpler than the system itself. So you need something that abstracts over the actual system state in a way that lets you understand both where there are opportunities to or requirements to do adaptation, but also what to do. And if the models are too complex, then that makes it very difficult. So architecture seemed to be a sweet spot that captures enough of the critical properties of the system, but at a level of abstraction that you could do reasoning and trade-off analysis.
Right. So we talked about the separation of concerns between the thing that's being controlled and the thing that's controlling it, the managed system and the managed system and the managing system. But you also, Owen, talked a little earlier about separation of concerns sort of within Stitch itself. So I wonder whether you think those issues might still be important, whether considering those kinds of things would still apply.
Yeah, I actually do think so. And I think building on what David already mentioned earlier, that there are actually two tiers or two levels of enduring principle. I would say that this is the sort of the inner tier of enduring principles. What we've figured out and embodying the concepts of Stitch is sort of separating adaptation into these different levels. At the very basic level, these operators are the primitive behaviors that a system can take, right? And then hierarchically at the next level, you want to have these tactics that invoke operators that become reusable units for different instances of systems of this particular family or style. And then you can have strategies that can combine these different tactics to tackle different quality dimensions, right? So these separating the levels of adaptation into these different concern levels actually is still, in my mind, very applicable and enduring for other cases. And ultimately, this lets us use utility theory to measure the quality of the outcome of adaptation. So, so we wrote this paper in 2006, and I basically wrapped up and finished around 2008, stated 2009. So I'm curious that in the intervening decade or so, how has this work impacted research in our group after that?
Well, let me take a crack at that. I think in many ways, Rainbow served a very important purpose in providing this framework of thinking about adaptation as a separate layer. If you break that down into its constituent components, you realize there's a certain amount of research that needs to be done in the various aspects of that. How do you monitor a system? How do you analyze the system state at runtime to discover problems? How do you do planning, and how do you actually do actuation? And in each of those areas, Rainbow sort of set the stage for a line of research. For example, in monitoring and analysis, you can ask, how do you do fault localization? How do you discover where the source of a problem is? In the planning element, there's been a lot of follow-on research going beyond what we did in the initial Rainbow. For example, looking at how do you reason not just reactively about what to do in the context of a particular problem, but how to use predictions about the future of the environment, the future of the system, to reason in a more nuanced way. Ways of using automated planners to come up with a plan instead of having them pre-specified. And also, in general, doing a much more nuanced understanding or creating a better understanding of how you reason about time. So in the early stitch, it was a very simple notion of settling time, but in fact, latencies are critical here in terms of understanding how certain adaptation strategies are going to have an effect over the system. We also have looked at what kind of planning makes sense and worried about how do you balance very fast but approximate planning with more nuanced but time-consuming planning efforts. So a lot of these things have simply taken each of the elements of what is needed in adaptation and sort of explored alternatives and in some ways more nuanced ways of approaching the adaptation problem.
Yeah, I think it's fair to say that the multi-objective aspect of the original work here sort of is a theme that sort of carried through for the last 14 years after the paper was written, right? I mean, the whole idea of planning using PRISM or analysis using PRISM has that idea sort of embedded in there, as well as uncertainty, but certainly the sort of balancing rewards or utility. And the work that you were talking about predictive tries to sort of do that trade-off at a longer time period. And even with the planning, combining planner stuff, we sort of think about that in terms of trading off the timeliness of the being able to do the plan with the actual effectiveness or the quality of the plan.
Right. I think there are two other dimensions, though, that you can look at what's happened. You know, one is the take-up of Rainbow as a system, where others have actually used it or built systems very similar to it, because it provides a good basis for doing research, and so others have found that it's a useful thing to build on. And the third area, I think, is the examples that we used, Owen mentioned, z.com or znn.com as it's called now, as a sort of a benchmark example. I think, you know, many disciplines require an example that everyone can get their teeth into that's both interesting enough that they can illustrate their particular ideas, but simple enough that pretty much anyone can go off and do it. And so this became, I think, in many ways for the community at large, one of the sort of basic examples that people would pick up and use to illustrate their approaches.
That's really awesome to hear about the impact of this beyond our group to the wider, basically SEAMS community, right?
Yeah, I would say, you know, the ZNN, that idea kind of seemed to capture something, some nice little sweet spot of a complex problem, but a simple manifestation. I think more recently we've sort of evolved that into the swim exemplar, which is sort of easier to install. One of the sort of original difficulties with ZNN is that it was a distributed system. And so you actually had to sort of work out how to, in a distributed way, install that system and run it, and what machines you had and all that kind of stuff. With swim, we have the same idea, but now it's sort of in a simulated network running on a simulator. And so the actual instantiation of Rainbow and the sort of exploration or illustration of the ideas is much simpler now.
So I'm curious, right? Thinking back over these 14 years, with our 14 years of experience and hindsight, so to speak, what do we think we got right with this paper, and what were the things that we think we could have done better or differently with our hindsight? David?
Yeah, well, I think this is related to the earlier discussion we had about what's happened to Rainbow since then, as we've sort of deepened our knowledge about what does it mean to build an adaptive system. But I think we made a number of assumptions justifiably at that time to get something going. One of them was the overall perspective that the real goal here was to replace humans, and a lot of our work was driven by that goal.
Right,
I think increasingly, as we look at adaptive systems as a class of autonomous system, we need to recognize that humans will continue to be in the loop, that they're not so much completely removed, but you need some way to incorporate them. And finding ways to think about humans in a sort of first-class way and how they interact with the automated adaptation mechanisms was something that we simply ruled out of scope in terms of.
Yeah, it was definitely a simplifying assumption.
Right. And we know, looking at autonomous systems in general, just how important it is to be able to reason carefully about when humans should be involved or not. So much of our current research, in fact, is focusing on that. For instance, how do you get an adaptive system to explain itself to a human operator, to build trust, or for the operator to detect when the system is maybe not operating as well as it should. Another thing that we did, again, to make progress, and given the perspective on administrators, was we looked at strategies as a fixed set of decision procedures.
Yeah.
And I think in hindsight, and partly because of the evolution of efficient reasoning engines and the incorporation of AI, we can look at how do you actually get the system to generate its own strategies.
Mm-hmm.
How do you get it to find good things to do, and hopefully doing as well as humans, but even better, of discovering strategies that humans might not have thought of, or being able to cope with situations that are very rare, where a human may not have already sort of worked out what needs to be done. Another area that I think we focused on that in hindsight could have been, or more recently has become broadened, is the idea of when is adaptation required or useful. And at that time, we were looking primarily at fixing problems. Server goes down or loads go up. What do you do to address the problem? But if you take a much broader view, you can say the whole approach can be much more homeostatic, in the sense of always looking for opportunities to improve the system. And that leads to a very different kind of control perspective, because instead of waiting for something to break, what you're doing is you're continuously evaluating the system to look for ways to improve it. And I think a lot of the recent research that people have looked at supports that, in the sense of finding ways to predict the future, look into the evolution of the system, and reason about alternative courses of action that might manifest themselves over time. And so that becomes, I think, an important new direction for this kind of system.
I see.
Yeah, and I think I'd also say that the design of Stitch seemed to be based on the assumption that the model that was being reasoned about was an architectural model, right? And
yeah,
that gets us a good way for sort of thinking about the kinds of problems that we were thinking about at the time. But systems are sort of more complex than just their architectural model, and in fact, you need to bring in a whole different kinds of models, environment models, maybe models of behavior, or models of missions if your system is trying to achieve some mission, like in a robot or something like that. And so sort of more recently, the work has been sort of extending those ideas as well. How do you incorporate multiple models? And they don't lend themselves, Stitch, doesn't lend itself as well to reasoning naturally about those kinds of models.
Another area that I think is sort of interesting to think about is when we built Stitch, in some sense, we were not just coping reactively, but dealing with the known unknowns, meaning that there were situations, uncertainties in the environment and the system that we might have to cope with. But we assumed that we could enumerate those. Those are the kinds of issues that we could be aware of up front, and then design our strategies around those issues. It becomes much more interesting in the long term of what do you do when you face some unknown, some quality or some requirement that you hadn't actually originally anticipated. So I think this becomes a big challenge now of how do you make a system that can adapt its own adaptation mechanisms over time. For example, you might have built your adaptation mechanism to deal with things like performance and cost, but now if suddenly later you realize you have to adapt with respect to security, how do you do that? How do you build in those mechanisms and without having to go back from scratch and start all over again in terms of thinking about your adaptation?
Yeah, that seems like a really hard problem, actually. And so we've actually covered the things that, you know, with our hindsight, we could have done differently, and wondering if what about things that we did right, in addition to the enduring principles that we've already discussed above.
Well, I think we've actually probably covered most of those. I mean, I think the fact that Rainbow still is around, you know, when you did a thesis, and unlike most PhD theses where the system gets stuck on the shelf and never gets used again, we have a good example of a system that sort of survived, maintained, and been improved over more than a decade. So in some sense, I think that speaks to having gotten a lot of things right in that system. So.
And I think definitely that sort of, we mentioned it, but sort of didn't highlight it. I think the sort of domain independence was the domain independent design, and getting the separation of concerns right in the way that we did enabled that longevity to be applied to different kinds of systems, to different kinds of situations, and sort of support this sort of broader research or broader cases. And I think that is certainly something we got right in Rainbow, although it does make Rainbow hard to reconfigure. You still get fairly easy adaptation for new systems. Yeah,
so I think we've actually had a really nice discussion so far, and kind of to round things out and close it off. Again, we're really happy and appreciative of the recognition of this 2006 paper. And I did want to give a huge shout out to my advisor and professor, David Garlan, for, in my mind, actually a foresight and vision on the overall architecture of this approach, pun intended, and also Bradley Schmerl for all the help that he's actually given through the years to, in a lot of ways, to mentor and to build out some of these ideas in order to see if they work, right? So I think this really took a village to achieve, and we are really happy for this recognition. Any closing words from Bradley or David, please?
Well, you know, I think for me, one of the most gratifying thing is when we started out, Rainbow was sort of out there as a kind of unique system, and today we have this SEAMS community where we have many such systems, and for me, the most gratifying thing is the way the community has come together as a separate, distinct kind of community that can focus on similar software engineering problems. And I think Rainbow is one of the stepping stones in that whole ecosystem of ideas and systems. So for me, it's really great to have seen those ideas come forth in this very much more general community.
Yeah, I'd like to echo that as well. I really enjoyed my time interacting with the SEAMS community, and it's been sort of very supportive of me and very inspiring to me professionally as well. And then, you know, Owen, of course, can't underestimate the amount of contribution that you made, and just sort of your general sort of positive attitude and your sort of go-get-iveness. I think really made this this whole Rainbow thing work longer than it normally would.